Hi, so welcome to this lecture where we will learn about a new topic. It's called the variation of parameters. It's a new way to find particular solutions to differential equations. We will, as usual, continue our studies with second order linear differential equations with some kind of an input on the right, okay? So let's just learn what this method is. As I said, it's going to be about finding particular solutions, but from a different point of view or with a new formula. Okay. So as usual, this is going to be our second order linear ordinary differential equation with f as the function of time, which is the input to the system, which is guided by this differential equation. Now we will refer to some of the new techniques that we have learned. We learned about the D operator method, and we can say now, after having learned that method, we can say that this differential equation can actually be written as this operator, okay, which really is an element of the ring of formal power series. We talked about this ring R D, okay, this ring of formal power series in D, okay, or infinite polynomials, if you can think of it that way, okay, and D here represented this operator, which is the derivative operator ddt, okay, and D squares, consequently was d2 dt2, which is the second order derivation operator, okay, and we said that this was the model that we had developed with C infinity functions, as x and f was supposed to be differentiable infinitely many times. So this is, as usual, you can go back to the lecture where we had developed this theory. I'm just reviewing it a little bit. So this x and f were parts of the C infinity function, and it turned out to be a module. The way we talked about it was the RD module, or the module over this ring of formal power series in D. But for now, for this lecture we will consider it as a model. As a module over C, or the complex numbers. We had R over there when we were developing this theory, but it can also be seen as a module, a CD module, okay? A module over the ring of formal power series in D over the field of complex numbers, okay? Really all the things that we have learned for this, because R is actually a subfield of C, so all those things that are valid in with C infinity as an RD module is also valid for C infinity as a CD module. The only reason we view this as a CD module now is because we're talking about roots of the auxiliary equation, which can turn out to be complex numbers. Okay, so for that reason, we just have to make that slight adjustment. You can, whether you actually think about the adjustment or not, all the things that we have learned with this as our C infinity as the RD module are all valid with C infinity as a CD module as well. All right, so let's just go over to the next point. So the way this can be factorized, because now you know that this is an element of the ring of this ring, okay, the ring of power series. Now, of course, I have replaced this by this now. So let me just rub that out. So think of this as an element of this, okay, the formal power series in D over the field, complex field, okay. So because this is an element here, and the way we had defined products and additions over this field, it turned out to be a ring. This CD turned out to be a ring, and so therefore all the laws of distribution and everything were true over there, and so by those things we can actually factorize this second order or second degree polynomial as a product of two first degree polynomials. Okay, just as, so if you write down the homogeneous equation, differential equation for this, it would be just with the right hand side as 0. Okay, and so the homogeneous, the auxiliary equation for the homogeneous part of this equation would be something like this, would be m square plus bm plus c equals 0. That's the auxiliary equation for the homogeneous part of this differential equation. And of course, if m1 and m2 are the true roots of the auxiliary equation, the left hand side can be written as m minus m1 times m minus m2, and the right hand side is 0. So really, if you look at it, this form is the same as this form, except that this is happening in real numbers or complex numbers. Okay, let's stick to complex numbers because the roots can come out to be complex numbers. So this is happening in the field of complex numbers, or the ring of complex numbers, and this is happening in the ring of CD. Okay, they are both rings, so they both follow properties. Just as this can be factorized, similarly this can be factorized. Okay, right. So therefore, if these are the two roots, and this is the only reason, because m1 and m2 can come out to be complex numbers, we have to view this as an element of this complex, this ring over the complex field. Okay, all right. So all three are the same things. Okay, these three, this one, and this one, they're all the same. They all have the same meaning. Okay, it's just different ways of writing the same differential equation. It's a second order linear differential equation, non-homogeneous differential equation. Right, and now I have this fourth point. Because I need this fourth point, it's a very important point, because this is what I need to find the formula for the variation of parameters. If m1 and m2 are the roots of the auxiliary equation, then the two homogeneous solutions, in other words, if you have the complementary function, the two terms in the two parts of the complementary function, the two homogeneous solutions of the homogeneous part of this equation were e to the power m1t and e to the power m2t. Let's just give them names. The one with m1, I'm calling that x1. The one with m2, I'm calling that x2. Okay, so these are the two homogeneous solutions of the homogeneous part of this equation with 0 on the right hand side. Okay, right. So as I said, for this method, we are basically finding out the particular solution for this differential equation. Now, as I said, the way you can find out the particular solution of this differential equation, so this is what I'm going to look at for now. Number 3, this is the form, it's the same form as this. So to find the particular solution, as we have discussed before, this is the element of this ring CD. So you can multiply both sides by the inverse of this element, which really was given by, the formula from the Taylor series. And anyway, we don't have to go there except to know that the inverse of this will exist, and that this is how we had written it. This to the power minus 1 was the notation in rings to denote the multiplicative inverse of this element. So if you multiply both sides, in other words, because it's a module, you act on both sides by this element. The left-hand side, because this is the multiplicative inverse of this element, this one acts on this, or this one multiplies this in this ring, to give you 1, okay? And that just leaves you with x, which we will call xp, because because xp will be the particular solution, okay? And the right-hand side, of course, this being an element of C infinity, will now get acted on by this element, CD. This element in the ring CD by this. This is the action we had talked about in the last lectures. So now what we have is, it's important to figure out, so to find out what is the particular solution, we just have to figure out what is this thing, what is the inverse of this element as an element of CD. It turns out that this multiplicative inverse of this element is going to be this element. Okay, the multiplicative inverse of d minus m1 times d minus m2 is going to be 1 over m1 minus m2 times this thing. The multiplicative inverse of this element minus the multiplicative inverse of this element. Okay. Now, of course, this one assumes that m1 and m2 are not equal. If m1 and m2 are equal, then this is not valid. But that would be the case of resonance, if you remember. If the two roots of the homogeneous solution or the auxiliary equation became equal, that was the case of resonance. But of course, the case of resonance was resolved by using L'Hopital. Okay. So, and the way we used L'Hopital was first assuming that they were not equal and then make one approach the other. So to resolve that case, we have to first know what would be, what would be the formulas when M1 and M2 are actually different. So that's the one we are going to work out. If we do come across a case where M1 and M2 are equal, we can actually resolve that case by L'Hopital as usual. So let's just do the case when M1 and M2 are not equal. Okay. So here we are assuming that M1 is not equal to M2. Okay, that's important one to note down here. Okay, all right. Now, so I'm claiming that the multiplicative inverse of this element, d minus m1 times d minus m2, is going to be this element. Now, how do I know that? Is because if this element multiplies this element and gives you the identity in CD, then this will be the multiplicative inverse of this. Okay, so let's just do that. We are multiplying this element with this element and we're supposed to get 1, which we get here. Let's see how. So again, by the laws of distribution in a ring, this multiplies this. Okay. Of course, this one multiplies this one. Okay. This is the multiplicative inverse of this first element, which makes the whole thing 1. Multiplication of this one on this one is 1. And then that leaves you with this element d minus m2, which I can write down here. Okay. One important thing here is that we are also using the fact that this is a commutative ring. In other words, you can swap positions in a multiplication. Okay. So yeah. So anyway, this one on this one is 1 and 1 on this one is d minus m2. Similarly, when you multiply this with this, well, you can first, as I said, you can swap positions. You can multiply this from the right also. So d minus m2 inverse on d minus m2 will give you 1, and 1 on d minus m1 will keep it as d minus m1. So really, when you apply the distributive laws in a ring, you get d minus m2 minus d minus m1, and as you can see, the d's will cancel. You will get plus m1 from here and a minus m2. That will, cancel with the 1 over m minus m2, and you're left with 1, which really is the 1 in complex numbers, but that really is the 1 in this module as well, and we have discussed that before. So therefore, multiplying this element to this element gives you the identity element in the ring, and so therefore this is the multiplicative inverse. So the multiplicative inverse of d minus m1 times d minus m2 is going to be this whole thing. Okay? Right. And in case anybody is wondering, I'm just going to rub, well, let's just do it here. This is really the idea of partial fractions, okay? Because this can be, so let me just rub this out. this is, why is this the idea of partial fractions, except that now we are doing it with the background that we have learned. So the idea of partial fraction, if I want d minus m1 inverse, d minus m1 times d minus m2 inverse, okay, that's just one, the way we have done our mathematics, or we have learned our arithmetic, is this is d minus m1 times d minus m2. If we think of these as numbers and not elements of this ring, okay, if you just think of them as pure numbers, real numbers, this is what this is. And this can be written as, it's a partial fraction. It's m1 minus m2 times 1 over d minus m1 minus 1 over d minus m2. Okay, that's the same simple partial fractions that we have learned all our life. Okay, you can see that d and d will cancel. You will get a plus m1 and a minus m2 on top, and that will cancel. And that's exactly what is happening here. Okay, this is the one. So this is the inverse. Okay, except that because this is now an element of this ring, we're talking in terms of the multiplicative inverse, and this is exactly this thing. Anyway, so let's just move on. So the multiplicative inverse of dm1 times dm2, d minus m1 times d minus m2 is going to be this element here, which I have written out over here, acting on f. So let's just, how does it act? Of course, it acts by, again, the same distributive laws. Okay, that's because this is a module. Okay, again, going back to what was a module. Okay, so if you have this thing, an addition of two ring elements, they will act individually. Okay, so this one acts on this, minus this one acts on this. Now, this one is a constant, it remains outside. Now, if you remember, what exactly is this? So let's just focus on this. D minus m1 inverse on f. Well, that's just a particular solution of a differential equation, which is this. If you remember. Okay. In other words, so this can actually be written as this is d minus, we're doing with m1. This is the particular solution of this differential equation, d minus m1y equals ft. This is the particular solution of this differential equation. I'm using a different letter y, not the same letter x here, because it's a different differential equation. This is the particular solution, and that's why I've written yp of this differential equation, which really is this. Okay, just multiply them out. That becomes dy dt minus m1y and ft on the right. Okay, and this really is a linear differential equation, and we have learned first order linear differential equations. We have learned first order linear differential equations. What was the particular solution? The particular solution was this. This was the formula. You multiply by this exponential of m1t, and there is going to be an integration where the input gets multiplied by e to the power minus m1. I'm using a dummy variable s here, some other variable, to integrate from 0 to t, because this is a function of t. So this is something that we have learned long time back when we were doing first order linear differential equations. This is the particular solution of this. So therefore we know this. This is the ypt. And ypt is this. So this really is this formula. So let's just write that. Excuse me. I'm going to rub out these things here. And I'm going to write, so this one, so from here on, this is just going to be 1 over m1 minus m2. This is this, okay? E to the power m1t, there's an integration from 0 to t of e to the power minus m1s times fs ds, okay? minus, well, the same thing happens with M2. There's no difference between M1 and M2 here, except that everything here that is M1 will become M2. So it's going to be e to the M2t, integration from 0 to t, e to the power minus M2t, s, the dummy variable, s, fs, ds. Right. So, now if I look at it, what's happening here is, I'm going to write this as, I'm going to take this inside this integral, okay? So, what I'm left with is going to be, so e to the power m1t is going to remain outside. And here in the first integration, I'm going to have fs. I'm going to bring this down with this negative will become positive, this index here. And I'm going to multiply that by, bring that inside this integral. So I'm going to have m1 minus m2 times e to the power m1s ds. Okay, and from this one I'm going to have minus e to the power m2t, integration from 0 to t, fs ds, m1 minus m2 times, I'm going to bring that down to e to the m2t. Okay. Now, I'm going to adjust this a little bit. I'm going to also multiply, I'm going to adjust the numerator and the denominator just a little bit. I'm going to write, instead of, I'm going to multiply for the first equation, for the first integrand, I'm going to multiply e to the m2t, s, both on top and down. So I'm going to have e to the m, so let's just, because I've written this, so this is going to be m1 minus m2 e to the m1s e to the m2s. Okay, that's, and I'm going to do the same with this one. So I'm going to have, I'm going to multiply m1 for this one, e to the m1s fs ds, and I'm going to have e to the m1s e to the m2s. Okay, I multiplied both up and down by e to the m1s for this integrand. Okay, and let's just make this plus, and I'm going to bring this minus in here. Okay. Right. So now we will look at this. Now, if you look at the denominator, it's a special thing. It's called, so let me just write it one more step. This, if you remember, was x1t, the first homogeneous solution, or one of the homogeneous solution, which I called x1. And this is 0 to t. This is x2 s fs. This is m2s. M2 was the second homogeneous solution, divided by, well, this one is going to be, I'm going to, let's just write it, m1 minus m2. I'm going to write it for now, but I will change this. This one is x1s and x2s ds. And for this one, this is going to be x2s 0 to t. This is going to be minus x1s fs ds. And this is going to be m1 minus m2 x1s x2s. Okay. Now this, I'm rubbing this out because I don't have the need for this anymore. This thing can be further given a better meaning. If you look at this particular determinant, it has a name, it's called the Wronskian. If you look at x1s, x2s, x1 prime s, which is the differentiation of x with respect to s, and x2 prime s, okay, this is going to be, well, let's just write out what this is. So this is going to be x1s, x2 prime s minus x1 prime s, x2 s. And what were they? These were exponentials. This was e to the power m1s, and this is the differentiation of the second, which is e to the power m2s, so that you would get m2 with the one-time differentiation, and this would be e to the power m2s. Minus, this one is e to the power m1 as differentiated one, so you would get m1 e to the power m1s, and then this one remains as it is, so you have e to the power m2s, and then that really becomes what? That becomes, so you can see e to the power m1s and e to the power m2s are common, and you're left with m2 minus m1, and this one, so e to the power m1s is obviously x1s, and the next one is s2s, e to the power m2s, okay? So therefore, this has, so this really is, if you look at it now, if I continue here, this is just going to be x1t integration from 0 to t. This is this determinant, which I'm going to call it by the name SWS, the Wronskian. S because it's a function of S, okay? It's called the Wronskian. This has a name. This determinant is called Wronskian, okay? And I'm going to call that by WS. So this becomes x2. So if you see this, there's a slight change of sign that we need here. This is m2 minus m1. So let's just, if I bring that, change the positions, I will get a minus x2 over there. So I'll get a minus x2s fs ds divided by, this is then the Wronskian, plus x2s integration from 0 to t. This negative sign will cancel if I change the positions of m2 and m1. So you will have x1s fs ds by, again, this will become the Wronskian. And that's the formula. Okay, that's the formula for the particular solution. Remember what we were doing, we were finding the particular solution all the way through, okay? And this is the formula for the particular solution. So what it tells you is this, that to find the particular solution, all you need to do first is to find the homogeneous solutions, which are easy to find, of course, because they are the solutions of the homogeneous part of the equation, and we know very well how to find those. Once you find the homogeneous solutions, the two homogeneous solutions, call them x1, x2, whatever you call them, the coefficients, or these are the varying coefficients, and that's why the name variation of parameters. The varying coefficients of, it's a function of t, as you can see that. The coefficient of x1t is a function of t. And similarly for x2s, sorry, this should be t. The coefficient is a function of t. To find this coefficient, all you have to do is to find the Wronskian, of course, that you know once you know the two homogeneous solutions. These are just the differentiations of them. And you have to multiply the input by, this rule. For the first one, you multiply that by minus the second homogeneous solution. And for the coefficient of the second one, you multiply that by the positive of the plus of the first homogeneous solution, and you find the answer. Okay, that's the method. Okay, so just as a problem, okay, if you think about it, and we have already done this when we had exponential inputs, if the exponential for a problem ft was e to the power at, what would be the solution, or what would be the particular solution for this? Okay, it would be, instead of finding this by our rules or the methods of undetermined coefficients, you can just simply apply this formula here. Okay, what would be the Wronskian? Well, the Wronskian would be this one. Okay, because your x1 and x2 were e to the power m1s and e to the power m2s. So that this was the Wronskian. Okay, and you can see that. Oh, the negative of this. The negative of this is going to be the Wronskian. So if I do this directly by the formula, this is going to be 0 to t. The negative of e to the power the second homogeneous solution. The right hand side is now an exponential input, so fs is e to the power as ds. Okay, and this is divided by, well, the Wronskian is m2. Here is the Wronskian, m2 minus m1 times this one, e to the power, this is e to the power m1s, e to the power m2s. Right? And for this one, it's just x2. Sorry, I missed this one. There's going to be x1, which is e to the power m1t. Okay, this is going to be e to the power m2t, and 0 to t. x1 is just e to the power m1s. fs is e to the power as ds, and divided by the Wronskian, which is m2 minus m1. x1 is e to the power m1s, e to the power m2s. And that, I think, we can work out quite easily. Well, first of all, this m2, e to the power m2s and e to the power m2s will cancel. The whole thing has a factor of 1 over m2 minus m1, which I can take out. So let me just take out 1 over m2 minus m1. E to the power m1t, doing the first one. This e to the power m2s and this e to the power m2s have cancelled. So you are left with, in the integration 0 to t, e to the a minus m1 s ds. Is that correct? There's an e to the m1s in the denominator. And so that gets a minus m1 when you add it to this index. Plus e to the m2 t, integration from 0 to t. Just the opposite thing will happen here. Okay, oh sorry, we forgot the minus sign here. There's a negative sign. So let me just put that negative sign here. Okay, this one will, e to the m1s and e to the m1s will cancel, and you will be left with e to the a minus m2 s ds. And we just have to work that out. I think that's quite easy to find out. We'll just work it out here. That would be, so this is 1 over m2 minus m1 e to the negative e to the m1t. Okay, what's the integration of this one? It's 1 over a minus m1 e to the a minus m1s integrated between the limits 0 to t, right? And the same thing is happening here. It's e to the m2t 1 over a minus m2 e to the a minus m2 s integrated or with limits 0 to t. Yeah. So let's just put the limits here. So this will be, so let's just work this out. m2 minus m1, there's a negative e to the m1t over a minus m1. And this is going to be e to the a minus m1t. And when you put that 0, you're going to get a negative 1 here. Okay. Plus e to the m2t over a minus m2. And here you're going to get e to the a minus m2 with a t and then a negative 1. Right. And so what happens next is sorry, I'm trying a new pen. This is not, it's fading. So this is going to be e to the m1t multiplies with e to the minus m1t, and that just cancels. They just cancel, okay? And so what you have is 1 over m2 minus m1. What you have is a negative. This multiplies, so this is going to be e to the a t. Okay, this one with this one have cancelled, and this a minus m1 in the denominator. There's a minus 1, so that gets you a, because this is multiplying all the way through, so this you're going to get e to the m1t over a minus m1. Okay, and then for this one, you're going to have this one, e to the m2t will cancel with e to the negative m2t. So you're going to be left with e to the at over a minus m2 minus e to the m2t over a minus m2. Okay, so let's just figure that out. So what do we have here? So what we have here is this one. You're going to have, so this one and this one. Okay, so I'm just going to write them separately. m2 minus m1. I'm going to collect these two terms. Okay, this one has 1 over a minus m2 minus 1 over a minus m1, and they are multiplied both by e to the at. Okay, so I've just collected these two terms together along with this one on the outside. Okay, and these two are on their own, so the same thing is going to happen to them actually. So I'm going to write plus, this one will multiply through, so you're going to have 1 over m2 minus m1 a minus m1 times e to the m1t minus e to the m2t with m2 minus m1 a minus m2. All right. Okay. Now, what about this? Well, I think what happens to this is going to be the a and a will cancel if you put them on top, if you put them in the numerators, and you will get a plus 2 and a negative plus m2 and a negative m1. So that will cancel with this. So what you're left with is 1 over a minus m1 and a minus m2 e to the at plus, well, these are constants. You can see, let me just give them some names. Let me just call them alpha e to the m1t plus beta e to the m2t. Okay, you see that this whole thing is a constant, 1 over m2 minus m1 times a minus m1, and similarly for this one. They're constants, okay? Right, and this you can finally write as, you can multiply this through, so you get a square minus m1 plus m2 a, okay, plus m1 m2, okay. But that's the same as, if you know, that's the same as, this is the same as m1 plus m2 will be the same as b, and m1, m2 will be the same as c, because these are the roots of this quadratic equation, m squared plus bm plus c. Okay, these are the roots of this quadratic equation. So you all know this from school. Okay, so this is just going to be, I'm just going to write that out straight away. Okay, so this is just going to be a square minus, sorry, this is going to be minus b. So minus, and this is going to be, so therefore plus a plus c. This whole thing is going to multiply e to the at, and here you have alpha e to the at m1t plus beta e to the m2t. That's it. So that's what the particular solution comes out to be. Now, if you work out the general solution, okay, the general solution, of course, you would have to add the homogeneous or the complementary function of the differential equation. The complementary function of the differential equation was going to be some constant c1 times e to the first homogeneous solution plus another constant c2 times another the second homogeneous solution. So this is a complementary function which we can write as h homogeneous. You remember that. Okay, so this is the xp. This is the particular solution. Okay, so if you add these two, you will get the general solution, xt. Of course, you can see that these two will combine to get you one particular coefficient for e to the m1t, and beta and c2 will combine, beta plus c2 will give you the coefficient for e to the m2t. So really, the way you can write this is some constant p e to the m1t plus q e to the m2t, okay? P here means alpha plus c1, and q here means beta plus c2, okay? This is one part of it, and then this part, which is 1 over a square plus ba plus c e to the at, okay? And this is a familiar solution. We have already done this before. This was really how the homogeneous part looked, and this was how the particular solution looked. And so in the general solution put together, this is what you get, and this is exactly what we had found before as well. Okay, so really, they all match. Okay, everything will match up to what we have learned, and that's why this theory stands. So this is just a flavor of how you can put this method of derivation of parameters to work. All you have to do is to follow the formulas, and you will get your result. Okay, and so this is just another way of looking at another way of finding particular solutions to differential equations, and here it is. All right, so thank you. We will take things forward in the next lecture. Thank you.